we now move on to our next block, where we will first discuss the concept of a process. As I had already introduced you to the process in operating system, a process is a program in execution. So when you write a program, say you write your C program for say adding two numbers, it is just a program, an passive entity. When this program is loaded into the memory for running, then this becomes an active entity. This active entity is known as the process. Thus, a process is a program in execution. The main difference between a program and a process are a number of factors that are associated with a process. So, a program is something that is kept on your disk on a file, while a process is kept in the memory. And there are different types of information that are associated with a process, such as every process has its stack that contains temporary data. If you had studied data structure, you must be knowing about stack. The stack is a data structure in which you can only take things out from the top of the stack. Also, you can add things at the top of it only. So, both input and output are done on the top. This stack data structure is used for storing temporary data related to a process. Similarly, the process is also associated with heap, which is the dynamically allocated memory to the process. Every process needs memory to store variables that are associated with the process. This heap and stack data structures can expand according to the need of the process. So, if there is a need of storing more data, the size of stack can expand, and similarly, the amount of memory allocated to the process during execution varies, and therefore, you can see the arrow here. Apart from this, the global variables of the process are stored in the memory. This part is known as the data section of the running process, and then comes the text part, which is the actual program code that you had written. So, your program just consists of this text part, while the process consists of this stack, heap and data that are again associated with the running process, but not with the program. Every process running in the memory passes through different stages. So, once the process is submitted for execution in the operating system, till its termination, the process passes through different states. These states can be represented with the help of a process state diagram. What you can see here is a general process state diagram, which describes the states that a process passes through during its lifetime. Let us discuss this in more detail. Once a process is submitted to the operating system, it is shown here in the figure as a new process. This process gets into the ready queue, which lies in the main memory. You know, whenever a process is executed, the task of execution lies with the CPU, and CPU chooses one of the processes that are available in the main memory for execution. CPU chooses these processes from a queue. This queue is known as the ready queue. Queue is a simple data structure, and the process that lies at the front or the start of the queue is selected for execution. The queue from which CPU selects the process is the ready queue. So, once the process is submitted into the main memory, the process simply goes into the ready queue. We will discuss more about the structure of this queue and how the processes are stored or represented in the queue later in this lecture. At some point of time, the CPU selects the process for running, Once the process is running, the running process might at some point of time get an interrupt. This interrupt could be from some other process. When an interrupt occurs, the CPU stops execution of the currently running process and services the interrupt. In that case, this process again goes back into the ready queue and the CPU starts processing the interrupt or starts servicing the interrupt. Otherwise, the running process might at some point of time requires to do some I/O, like the process might print something on the console. This requires an input-output operation that accesses the console and prints the content on it. When this happens, the process goes to the particular device and waits in the device queue, and in that case the CPU simply switches to another process, and therefore this process stops running and gets to the waiting queue. Once this I/O is or the event for which the process was waiting, like the process might fork a child process and the child process might execute and the parent process might be waiting for the child to execute. In that case, the process would switch its state from running to waiting. Once this process is waiting in this waiting queue and the event for which the process was waiting has completed or the I/O has been completed, the process now goes back to the ready queue. Notice that after the event has been completed, the process does not go back to the CPU again. It goes to the ready queue, and as per the priority decided by the scheduling algorithm, the CPU later again selects this process from the ready queue. So whenever the process it goes into waiting because of say some interrupt or because of completion of some event or I/O, the process will get back into the ready queue and it will be selected later on by the CPU again. This sequence continues until the process has terminated either normally or abnormally. In any case, the process exits from the system and it is labeled as terminated. So this is the lifetime of a process that is running in your operating system. Every process that is running in the memory or every process that has been submitted to the system and it is kept in the main memory is associated with a number of information. Say the amount and the number of registers associated with the process, the data that is written in the registers, the variables that are associated with the processes that may be present in the main memory or the registers, the files that the process might be accessing. So there are certain types of information that need to be kept when a process is running. All these information are kept in what we call as a process control block or a task control block. So a process control block contains all the information that is associated with a particular process. These are process state, so in what state presently the process is, then the process number. Every process is identified by a number. So process number is associated with the process control block of every process. Then the program counter, which essentially tells us the next line of code that will be executed. Then the registers, the information stored in the registers associated with the process. Then there are memory limits. So the amount of memory that the process can legally access, this memory has a lower and upper limit, which is also stored in the process control block. Then a process might be accessing different files on the hardware, on the disk that are stored on the disk. So the list of open files is also kept in the process control block, and there are further some other information like accounting information, etc., that are kept stored in the process control block. So you might understand process control block as something that contains all the information that you might want to know about a running process. So if you have the process control block associated with the process, anything that you might need while the process is running, will be available in this process control block. These process control blocks play a very important role in context switching, because in context switching, when the CPU is running one of the processes and somehow stops running it and chooses some other process, then all the information associated with that process need to be saved, and these information are available in the process control block, which the CPU can later access to again run that executing process. Let us discuss the concept of scheduling in more detail. As I already told you, once a process is submitted to the system, it is loaded into the main memory. In the main memory, the process is kept in a ready queue. From this ready queue, the CPU selects a process for execution based on a proper scheduling algorithm. Once the process is selected, it keeps running until one of the following happens. Either the process stops for an I/O request, for handling an I/O request. In that case, the process goes into an I/O queue that is associated with the particular device that will service that I/O. Otherwise, in case of time sharing systems, the time allotted to the process for running might have expired, because of which the process will again keep waiting in the ready queue until it again gets time for execution. A process might also fork a child and wait for the child to execute. In that case also, the CPU, the process is not then deallocated from the CPU and it's kept in a ready queue. Until the child executes, the process keeps waiting. And in the fourth case, an interrupt, which is an external event, happens and the CPU has higher priority for processing the interrupt, and therefore the process is kept again in the ready queue until the interrupt is processed. In all such cases, when these events that caused the process to be deallocated from the CPU, when these events complete, the process again goes back to the ready queue, and according to the scheduling strategy, CPU at some point of time selects the process from the queue for further execution, and this goes on until the process completes execution and terminates. Now, you have by now understood that the processes are going to be kept in the ready queue and will be selected by the CPU for execution. Similarly, in batch systems, the processes are submitted to the operating system before execution of any process. So, all the processes are submitted once. The selection of which processes are to be kept into the main memory, the processes are actually loaded from the disk by a scheduler, and the scheduler is responsible for keeping these processes in the main memory, that is the ready queue. This is the task of the scheduler, to select processes from the disk in case of a batch operating system, where all the programs are residing on the disk and the scheduler would choose one of the processes to be kept in the main memory. Again, there is a scheduler in this ready queue which selects the processes for execution into the CPU. So, one of the scheduler was selecting the processes to be kept in the main memory, that is the ready queue, and one of the scheduler was selecting the processes for execution by the CPU. The first scheduler is known as the long-term scheduler, and the scheduler that selects processes for execution by the CPU is known as the short-term scheduler. The main difference between the long-term and the short-term scheduler is in the frequency of selection. In case of a long-term scheduler, it selects the processes for keeping in the ready queue, and this decision does not have to be very frequent. So, after some point of time, once a process has completed its execution and has terminated, the long-term scheduler will get invoked and select one of the processes from the pool of processes that are residing on the disk. While during execution of a process, one of these events might happen at a difference of very short time, and therefore CPU scheduler needs to make a quick decision regarding which next process is to be chosen for execution at the CPU. Therefore, the short term scheduler needs to decide quickly about what processes are to be selected, and therefore the scheduling algorithms for both the long term and short term schedulers are different. The long term scheduler also controls the degree of multiprogramming. You know from your previous lectures that multiprogramming operating systems keep running processes all the time in the CPU. So, the idea is to keep the CPU working all the time and not to keep it idle. The number of processes that can be run by the CPU are basically dependent on the amount of processes that can be held in the main memory. We are right now not talking about the concept of virtual memory. So, we are supposing that all the processes are actually residing in the main memory totally. So, the number of processes that can be held in the main memory will decide the amount of work that we can expect the CPU to do. And therefore, since the long term scheduler is deciding the processes and the frequency by which the processes enter into the main memory, it is also considered to be responsible for controlling the degree of multiprogramming of the operating system. Further, it is the responsibility of the long term scheduler to select processes in an appropriate manner. For example, there are certain processes that are known as CPU bound processes. These processes spend most of their time in executing on the CPU and spend very little time in doing I/O. While there are certain other types of processes that are known as I/O bound processes. These processes spend most of their time in doing input and output operations, while less of the time is used in execution at the CPU. Suppose the long term scheduler chooses only I/O bound processes. What will happen in that case? The CPU would be idle most of the time, because every time it selects a process for execution from the memory, the process will keep waiting in the I/O queue for doing some kind of I/O. While on the other hand, if the long term scheduler selects processes that are mostly CPU bound, then all the processes will keep waiting in the ready queue, because they will execute for only the time slice that they are provided with. Or in that case, or in other cases, if there is some other type of scheduling algorithm that is being used, most of the time one of the process will keep using the CPU and other process might not get a chance to execute. And therefore, it is important for the long term scheduler to select processes in such a manner that there is a good mix of CPU bound and I/O bound processes, so as to give the illusion of multiprogramming to the user and keep the CPU busy all the time. Then comes the short term scheduler, where the task of the short term scheduler is to select some process from the ready queue for execution. As we have discussed, short term scheduling algorithms are different, and the selection is, the main idea is to keep the task of selection as simple as possible, so that the processes can be selected quickly for execution. In case of time shared systems, where we have some users using the systems on a time shared basis, we usually do not have long term schedulers like in Windows operating systems. In these types of systems, the program, once a process is submitted by the user to the operating system, it immediately goes into the ready queue and starts executing. Suppose there are a lot of processes that are present in the ready queue. Then, since there is no long term scheduler, eventually the performance of the system will degrade. In such systems, like the time shared systems I discussed, it is assumed that if the performance of the system degrades below certain level, some of the users will simply quit, and therefore the users will themselves adjust to the system, and some of the processes will be removed automatically from the system, and then the performance will then get better. Therefore, there is no need for having a long-term scheduler as such, while short-term schedulers are always present in every system. There is another concept of a medium-term scheduler, which is present in some of the operating systems. Wherever present, the medium-term scheduler lies between the short-term and the long-term scheduler. The basic idea behind having a medium-term scheduler is to swap some of the processes from the memory when the performance degrades. So, suppose there are a lot of systems that are present in the main memory. The short-term scheduler will select some of the processes to be kept out of the memory and executing the remaining of the processes. This process is known as swapping. However, medium-term schedulers are not present in most of the operating systems. Another concept related to processes is the context switching. In context switching, basically you know that in a multi-programming system, suppose we are having a single CPU. In that case, the CPU can only execute one program at a time. But we know that processes not always keep executing using the CPU because they might be waiting for some event or some I/O. In multi-programming systems, we want to keep the CPU busy all the time, and therefore, when one of the processes that is running stops, actually it waits for some I/O or some event to happen, we select some other process for execution, and thus the system gives an illusion to the user that more than one processes are running at the same time. Doing this in fact requires some type of support from the operating system. When we stop a running process because of some I/O or it keeps waiting in the ready queue, some other process is selected. But before we can do this, we need to save some information related to the process so that the process can be invoked later. We have already discussed that the process control block of a process contains all the information that are associated with a running process, and all the running processes that are present in the ready queue have their process control blocks. In fact, the ready queue is a linked list which contains links to the process control blocks of all the processes that are present in the main memory. So, once the CPU decides to stop executing the current process and put it into the waiting queue and select another process, the first thing that the CPU does is to save the context of the running process. This context is saved in the process control block, and the context of the another process that is selected is loaded from the memory. This context is available in the process control block of that particular process. The switching process requires saving the state of the current process and loading the state of the present process that is chosen for execution. This process of saving the state of the current process and loading the state of the another process is known as context switching. Context switching is pure overhead over the system, because while switching the context, the CPU is not doing any useful task. The CPU simply saves the context of the present process and loads the context of the process that is next going to be run. And therefore, context switching has to be quick. Context switching depends on various things. Apart from hardware support, it is also dependent upon the complexity of the operating system, the type of information that the operating system keeps with every running process, because all the processes have their process control blocks, and all the information that are required for running a process are always saved before switching the context or before selecting another process for running. Some type of hardware support can make this process easier, as some of the operating system provide more registers, and therefore the information related to registers need not to be saved into the memory for emptying the register so that it can be used by some other process. But even in those cases, if the number of processes that are running is more than the number of registers, then again we will have to resort to saving the contents of the registers into the main memory. Now we have discussed the concept of context switching, why is it important and how is it an overhead over the system. We discussed about different types of scheduling queues and schedulers. Thank you.